Hello, everyone, and welcome to the October 2021 edition of Astronomy on Tap, and we are coming to you live from Baton Rouge. We know it's been a couple of months since we last had a show, so we are very happy that you are all here with us today. You may have noticed that we are still online, even though we were planning to be in person at this time. So if you would like to see us again in person, we do ask that you would get your COVID vaccine if you haven't, and encourage your friends and family to do the same if they also haven't done so. But anyways, this month we have two wonderful speakers from out of town for you, so please get ready. Before we get started, here are the usual ground rules. Of course, as always, be considerate in the chat. We never have any issues, but it's always worth mentioning. At any time during both of the talks, feel free to drop any questions that you have for the speakers, and I will field them to the speaker after the talk is over. In the meantime, during the show, please consider donating to our Venmo and PayPal. Those two things are the way that we keep the show going and the way that we are able to bring you merch and all that kind of fun stuff. As per usual, we like to add a little competition to our donations. So this month we want to know, which is your preferred asteroid defense mechanism? Is it a giant laser, or would it be more like a giant trampoline? And if you choose to make a donation, you should write your answer to that question in the memo section, and we'll log that for you. Last thing, please like this video if you're watching and subscribe to our YouTube channel. Both of those things help us so much, and they help us get our show out to more eyes. So without further ado, we'll move right on to today's talk. Our first speaker is joining us from Vancouver Island. He was schooled as a historian, but now works as a science communicator, writing for Universe Today and Interesting Engineering. In addition to his love in science and science fiction writing, he also enjoys things like historical beer and is a lifelong practicer of Taekwondo. So he's here with his talk titled The Coming Age of Space Exploration. Please welcome Matt Williams. Matt, you'll have to unmute.
Hello.
Hello. We also can't see your face yet, so.
Okay. Well, that's fine. You probably don't want to look at me anyway.
Oh, and
yeah, let me just, sorry, one sec. Bring this up here now. And yeah. Okay. So thank you for there we go. Thank you for that introduction. And yes, I'm Matt Williams. I'm a science communicator, and today I'm very happy to be speaking to all you who are listening after the hiatus. Basically, what I want to talk to you about today is where we're going with space exploration, because it's sort of a general understanding today. We're in a whole new age of space flight and activities in space, and there's a lot of plans and a lot of talk. But if you sort through it all, it's really a very exciting time to be alive. So, to begin, a term that is often thrown around these days is Space Age 2.0. Are we living in Space Age 2.0, and what exactly does that amount to? And well, for starters, yes, we are. And the reason we're able to use that term there is because we're now living in an age of activity where we have a level of activity in space that hasn't been the case since the Apollo era. And whereas the Apollo era was characterized by two superpowers trying to get to space and beat each other to space, the new era is one where competition is still very much a part of it, but cooperation accounts for a lot more now. And there are a lot more participants. So getting to where we are today, it does require a little bit of retrospective there. So basically everything we did in the post-Apollo era led us to now. And that was characterized by, as soon as NASA had finished sending the last of its 6 crews to the moon, 12 astronauts in total. And that was by 1972-73, the Apollo program was declared finished. The Soviets had already conceded the moon to NASA. And so now it was understood. We need to start taking the next steps. We need to start thinking of the next goals. And due to the changing budget environment on all sides, it was understood that, well, since we spent all this time and energy getting to space, now we need to focus on staying there. So we need to develop the technologies that are going to cut the cost of going to space and also ensure that we can live in space sustainably and safely and so forth. So throughout the post-Apollo era, that meant space stations and also the development of reusable spacecraft. And so in terms of space stations, that gave us, on the Soviet and Russian side, they took an early lead. And they started deploying what were known as the Salient Stations. And these were small stations, crews of 2 to 4, I believe. And there was several of these deployed between the early 1970s and the 1980s. And they provided a lot of experience and expertise, which then went into the development of Mir, which was a large modular station. So basically that means it consisted of several modules placed together in orbit, and many that were based on the design of the Salients. And the NASA did the same with Skylab. It was a relatively small station there, and the purpose was to develop all the necessary experience and expertise for the next big step. And originally NASA hoped to build its own station to compete with Mir. But by this point, the cooperation I referred to, it now began to really manifest itself. So the Soviet Union was now collapsed. It was Russia and NASA. They began working on the ISS, and many other space agencies joined them. And what was intrinsic to the ISS, coincidentally enough, was the space shuttle. Because this was the other aspect of the post-Apollo era, developing spacecraft that could be reusable, at least in part. And for NASA, that yielded the space shuttle, whereas the Soviets, who were still the Soviets at the time, they created the Buran space shuttle. And you probably heard of that one. It's become the focus of interest again in recent years. It's very much like the space shuttle, and it never quite materialized because of budgets, and the collapse of the Soviet Union quickly followed. But yeah, the space shuttle was intrinsic to assembling the ISS, and from that point onward, commercial space began to enter the fray. They became the partnerships between space agencies and companies became a lot more common, a lot more lucrative, a lot more widespread. It wasn't just about building rockets anymore, but providing services, delivery services, satellites, you name it, and even today, launch services. And as for the agencies, you need look no further than the ISS to see just how many have become involved. But some major players are the ESA, that's the European Space Agency, Japan, which is JAXA, China, denoted by CNSA, India, which is the ISRO, and most recently, the United Arab Emirates. They launched their very first mission to Mars, and it was the first space mission launched by an Arab nation or a nation in the Middle East and Central Asia. And as I said, commercial space has come into the fray too, and they've come in a big way. And includes reusable rockets, which was Elon Musk's contribution, and also Jeff Bezos. They both began at about the same time trying to develop reusable vehicles, and also small satellites or CubeSats, which vastly increased access to satellite technology. So now the question is, now with all this under our belts, what exactly are the next big steps that NASA and other space agencies are planning with commercial partners? And there's quite a few, and the first step in this is going back to the moon, or in the case of non-NASA space agencies, going there with crew for the first time. And right now for NASA, that takes the form of Project Artemis. And I'm going to start this little video here, which This shows us the European Space Agency's big mock-up for a lunar base. And yeah, by the time it gets to the interesting part there, we'll be talking about it. So Project Artemis, that's the culmination of everything that NASA's been doing since about 2004. And that means new heavy launch vehicles for the first time since the Saturn V in the Apollo era. And that's now known as the Space Launch System. And new space capsules that are updated and improved versions of the old Apollo spacecraft. And that's the Orion Multipurpose Crew Vehicle. And so the plan as it stands right now, the timeframes are once again kind of being moved around. NASA doesn't think 2024 that they're going to land astronauts by then. But yeah, the same overall long-term framework is there. So from now until 2032, they want to start sending crews back to the lunar surface. They want to build a base camp on the surface. And they want to pair all that with a space station in orbit known as the Lunar Gateway. And this will facilitate trips to the moon and long-term stays on the surface and the ability to use that infrastructure to go to the next big leap, which we'll get to in a minute. And as you can see from the video here, this shows astronauts with the European Space Agency. They have SpaceX-like outfits on. And they're deploying modules of the International Lunar Village, and this is the ESA's plan, very similar to the to the Artemis base camp. But the purpose of this is not part of any one program; it's to be the successor of the ISS. And unfortunately, China and Russia are not participating in this. They instead came together to launch their own, which they call the International Lunar Research Station. And like I said, it's unfortunate. It would be nice if, in fact, there could be an ISS type situation on the moon, and that may still happen. But in the meantime, even though there's likely to be multiple bases, they're all being built in the same general area. And they're all based on the same considerations and ideas and technology. And that's the South Pole Aitken Basin, which is the southern polar region of the moon. It's heavily cratered, and within those craters, they're permanently shadowed. So there are these nice cold sinks on the moon, and they're able to keep water ice that's been deposited there on the surface in stable frozen condition there for eons or even longer, and there's quite a bit of it. So the plan has been now for many years since all this water ice was confirmed that in these craters bases will be built. They'll use 3D printing and local regolith or moon dust to create the bases. And they'll have partially inflatable modules, like you saw them deploying here, and they'll be safe from temperature extremes and from exposure to space. But of course, they'll also take advantage of the abundant sunshine above the crater rims, and they'll have access to abundant water. And from that comes the next step in the game, which includes multiple proposed missions to Mars. Right now, there are, I believe last count, there was 11 or 12 operational missions on Mars or in orbit around Mars, and representing several nations, not just NASA or Russia. And so in the coming years, there are many that are planned. The fleet right now, you have multiple NASA rovers on the surface. Russia has not really sent a Mars rover back since the early space race, but they will be. They'll be sending a lander, which will be part of the ExoMars 22 mission, and that mission will include the European Rosalind Franklin rover. And that will launch in 2022, as the name suggests. The Indian Space Agency, ISRO, they want to send a second orbiter, because they've got one right now that they managed to put around the planet on their first try. That was quite the accomplishment. China has many too now, and that included their first mission to Mars, included 3 separate robotic elements. So India is going to follow up on their success with a second orbiter. The European Space Agency in Russia is going to send another sample rover to the surface. And NASA and the European Space Agency, they're going to collaborate on bringing samples back. This Perseverance, which I'm sure people have heard, it has its whole sample caching system there, and it's been obtaining drill samples on the surface, which is it's going to leave behind. And so in the coming years, the sample return mission will land on the surface, pick them up, and send them home. And the results of the research there are expected to be absolutely fantastic and unprecedented. Now, these missions are also intended to pave the way for crewed missions, which are, right now there's only two space agencies that want to conduct crewed missions, and that's NASA, and as recently announced, China. And nevertheless, it's very impressive that more than one space agency is talking about this. So NASA's Moon to Mars, or previously known as Journey to Mars, it would be using all of the architecture of the Artemis program to then go the step further there. So with the SLS and the Orion capsule, they hope to launch astronauts to the Lunar Gateway, who would then restock, resupply, and then merge the Orion space capsule to what's called the DST, or the Deep Space Transport. And with the Orion attached on front and this big spacecraft there that uses solar electric propulsion, they then fly to Mars. And ideally, they want to have a second orbiting habitat there too, so that they can dock with that, take a lander down to the surface, come back up when they're done. And the idea here is you don't have to bring all of your fuel with you, which is the single greatest source of mass on a mission. And the architecture there that they've created would also mean that, we can keep going back. We don't send a handful of missions that are all very, very heavy, very expensive. We've got all this reusable stuff that's going to allow us to do that. And of course, they want to build somewhere where there's lots of water ice and then use that, and also the Martian soil, just like they plan to do on the moon. 3D print out habitats, and all that whole process is known as in situ resource utilization, or ISRU. And that's a big buzzword in all space exploration right now, so definitely remember that one. So China's plan, it's similar and it parallels NASA's. They want to begin launching flights every 2 years for when Earth and Mars are at their closest during an opposition. And so starting in 2033, then a mission in 2035, 37, 41, possibly beyond. They want to send crews to the Martian surface, who will then begin the process of building a base. This is it's a rather ambitious plan, and it does move up China's proposed timetable by at least a decade. So far their plans had been to focus on the moon, not think about Mars until the 2040s. And of course, commercial space has its own plans. That includes Elon Musk, who also wants to conduct crewed missions to Mars, and his is actually a standalone architecture. He wants to finish developing the Starship and the Super Heavy launch vehicle, and he would like to have, he's spoken about this rather openly, he wants to have a fleet of as many as 1,000 Starships launching, and or conducting 1,000 launches a year, just launch, retrieve, repeat, until he can send 100 megatons and 100,000 people to Mars. Oh, that's a slight typo there. He also wants to make launches to Mars every 2 years, but he's not going to be sending that much stuff every 2 years. That's the overall goal. So yes, ultimately he wants to send that many people to establish a colony, a Mars base Alpha, and create the first self-sustaining city on Mars. And Jeff Bezos, who a lot of what he has planned actually is not really talked about much these days, mainly because he's rather far from realizing it. And yeah, Blue Origin has fallen behind SpaceX a lot in years, but he does have a very bold plan too, and he actually got started on it a year before Musk did, and he calls it building a road to space. And the idea is that the rocket family, the Blue Origin rocket family, and they all have the name New affixed to them, using the New Shepard, conducting space tourist launches, making that into a viable industry, using it to fund the creation of more rocket infrastructure, and then with the New Glenn, which is an orbital class vehicle, and the New Armstrong, which is a lunar class vehicle. Then start sending people and payloads out further and further. And he ultimately wants to have all this in place so that he can create habitats all around the Earth-Moon system and beyond that could accommodate as many as 1 trillion people. So human civilization, you'd like to see the numbers go up to 1 trillion. And by harnessing the resources of space, yes, it's resources for all. Post-scarcity society. And Richard Branson has got a similar dream. He wants to use his Virgin Galactic and these suborbital flights and keep doing it until it becomes much cheaper and more people are able to do it. And basically making space more accessible, democratizing it, and letting more people have the chance to take part in the experience and experience the effects of it, which are profound. And of course, plenty has been said about asteroid mining. That is a real plan, and no clear dates are yet available on that. But as all this space infrastructure that others are talking about are created, then there are several companies that want to prospect and harvest asteroids for all their mineral wealth and their volatile elements, do that in orbit, and just the amount of wealth that we could extract from that and materials would, again, usher in a post-scarcity world. And it's also rumored, it's been said that when the world's first trillionaires are here, when they're around, they'll undoubtedly be involved in asteroid mining. Which actually plays right into this next mission. So while all this is going on, going back to the moon to Mars, there are missions proposed for the asteroid belt and to study other asteroids like the Trojans, which are part of the asteroid family that follows in Jupiter in its orbit. And there's a mission known as Lucy, which is a NASA mission. It actually launched just the other day, and it will arrive. It will stop in the asteroid belt. It'll do a flyby one asteroid, and then it will rendezvous in Jupiter's the Jupiter system by 2033, and it'll study the Trojan population. And the reason why these and other asteroids are so interesting is because they're leftover material from the early solar system. After the planets had all formed, these leftover bits essentially fell into their orbits like they have today and have remained largely unchanged. And so, yes, scientists, they want to get a look at them. They want to see what the early solar system looked like through these objects. And another NASA mission, Psyche, this is going to go to the main asteroid belt. It's going to rendezvous with a body of the same name, Psyche 2 it's called. And it's very fascinating because it's a metallic asteroid. And metallic asteroids have been known to exist, but they're predominantly metallic, whereas Psyche is not only very, very big, it is also almost entirely made of metal. So in fact, astronomers believe that it's not really an asteroid, it's the remnant of a planetoid. And something that formed in the very early solar system, and most likely, the consensus is that it got slammed, major impacts, which caused its outer layers, its rocky layers, to just melt away, leaving this metallic core behind. And since everything from Mercury to Venus to Earth to Mars are all composed in the same way there, metallic cores surrounded by silicate mantles and crusts. This would be a way to study how cores are formed and what secrets they might have about planetary magnetic fields. And just an awful lot of research to be done there. And it's going to be starting by 2026 when the probe arrives. And not for nothing, but it is estimated that asteroid too is worth trillions of dollars alone in precious metals. And beyond the asteroid belt, there are plans now to explore what are often referred to as ocean moons. And there are many in the solar system. And they all have one thing in common. They've got icy surfaces and interior oceans. So they've got the conditions in their interior to maintain warm water oceans. And there's all kinds of hydrological activity and all the basic elements of life are in there too. And so NASA scientists first realized this about Jupiter's moon of Europa in the 1970s when the Voyager missions got a good look at it. And so they've been wanting to go back ever since. And but in the meantime, it's been realized, well, Ganymede, another one of Jupiter's larger moons, it has the same thing going on. Callisto may have the same thing going on. And then beyond that, the outer solar system is filled with these moons. So next year, the European Space Agency is going to be sending an investigative probe. And it's called the Jupiter Icy Moon Explorer, or abbreviated JUICE. And it's going to go to Ganymede, and it's going to study its surface. It's going to probe its depths with radar and magnetometers and try to figure out its interior structure and really confirm if all the ingredients for life are there, if the ocean's really there and that. The Europa Clipper is going to leave in 2024, and it's going to go directly to Europa. JUICE is actually going to fly by Europa near the end of its mission there. It's got 2 proposed flybys. So Europa is going to get a lot of attention because we know almost with complete certainty that there's an ocean beneath its surface. We've seen plumes coming up from the ice, evidence of cryovolcanism, and that those plumes connect directly to the interior ocean. And so scientists want to send an orbiter to Europa to watch these plumes, look at the surface, and see if there's any indication of life in there, any kind of biomarkers. And the Clipper is also going to survey the surface and conduct all kinds of vital science activity, one of which is to scope out a landing spot, a potential landing spot, for a third mission called the Europa Lander, which is tentatively dated for 2030. Now, this mission will pick up where Clipper left off. It'll land on the surface near the plumes, and it will attempt to study the plumes up close and the surface around them to see if, in fact, there's any simple life forms, bacteria, or indications thereof that are coming up from the depths and then landing on the surface, and try to examine them before they freeze up or die from radiation. And Saturn, of course, not to be left behind. Saturn also has many ocean moons, and 2 in particular are in Enceladus, or I've heard it pronounced both ways, Enceladus. And that's down here at the bottom there. That's the graphic. It shows its interior ocean and the plume activity that comes right up from the core mantle boundary. And Titan, Saturn's largest moon, which not only is thought to have an interior ocean, but it's got actual lakes of methane on its surface and a very dense atmosphere. And it's got a very, very rich organic prebiotic chemical environment. So scientists are actually curious if there's any kind of life forms there, because it's like the ingredients are there, just seems too cold, but it's hard to say. Who knows what conditions life could actually emerge under. So the top image there is the Dragonfly. That is a firm mission now. It's going to launch in 2027 and arrive on Titan by 2036. And it's going to, many proposals were considered, and this was considered the best bet, NASA wanted a mission that could sample the atmosphere, the surface, the hard surface, and also go to those methane lakes and sniff around on them as well. And it's nuclear powered, so it would be able to fly there autonomously on its own for many years, which is necessary because Saturn being very far. And in the course of that, it's going to try and confirm. It's going to just try to teach us all it can about the Titan's environment. And Enceladus, there's no firm plan yet for a mission, but a lot of proposals have been made, and they generally go by the name the Enceladus Explorer or the Enceladus Vent Explorer, which is my favorite. Now, the idea there is, well, Cassini, when it was flying around the Saturn system, it looked at Titan. They tried to deploy a lander there, the European Space Agency one, but it ceased functioning when it hit the surface. And Cassini also got a pretty big eyeful of Enceladus and its plumes and what it did. Unfortunately, it couldn't really get close enough to really study those plumes. So yeah, the Eve Explorer would fly to Enceladus, establish an orbit around it alone, and it would do its best to pick up samples or just get really close enough to scan them and look for biomarkers there too. Because if there is life inside there, it is a very good bet that indications of that are going to be periodically spewed out by these vents. Now, sorry. And on top of all that, there's also going to be some astrophysics missions coming very soon that are going to be very, very, very exciting. And I was just writing about this earlier today. The James Webb Space Telescope has been unboxed. It was delivered to the spaceport in French Guiana, where it's going to launch on a European rocket. And yeah, they unboxed it and are getting it ready. And the date is now set. It's going to launch on December 18th of this year, after so many delays. And it will be the most complex and the largest, most powerful observatory sent to space to date. And what sets it apart is it's got this very large viewing device there, those hexagonal mirrors that form its primary mirror. It's got a sophisticated sun shield to keep it cool, and some very, very sophisticated near and mid-infrared optics and spectrometers. So it's going to be able to take in light from the cosmos in the infrared wavelength and scan for biosignatures and signs for life on exoplanets. It's going to be able to see all through cosmic dust to get a better sense of our galaxy and other galaxies. It's also going to be able to see planets forming from dust disks, and it's in rather incredible range, which is superior to that of Hubble. It's going to be able to see far enough back in time to see the first stars and galaxies that were forming after the Big Bang. So it's going to be able to tell us all kinds of things about the evolution of galaxies and stars. And the exoplanet contribution there, it's going to be able to look at exoplanets and obtain spectra by examining the light reflected directly from the planet atmospheres. It's very hard to do in visible light, but in infrared, it's easier, as long as the observatory is sensitive enough and sophisticated enough. So by examining that light directly from planet atmospheres, it can tell us what's in the atmosphere, which is something we really haven't been able to do with anything other than massive gas giants so far. So that's going to be very helpful in determining whether or not any of the thousands of exoplanets we've seen so far are actually habitable. European Space Agency will be launching the Euclid Probe next year, and it's got a powerful primary mirror, and it's going to measure how fast galaxies are moving away from us and from each other. and to probe backwards in time to 10 billion years ago. So still in the early universe, and by seeing how the universe has been expanding in all that time, it's going to be able to shed light on basically the missing mass of our universe, which is known as its dark matter theory. And by measuring the rate of expansion and how that's been accelerating over time, it's going to determine what the role is of dark energy, or, of course, whether or not dark matter and dark energy even exist, or we're just, we need to revisit the laws of physics as we know them. And last, a very exciting mission again, is the Nancy Grace Roman Space Telescope. This mission is the direct descendant of Hubble. It's got a similarly sized mirror. The design is similar in many ways, and it's named after NASA's first chief astronomer, Nancy Grace Roman, who was, she was a woman working in astrophysics in a senior position at a time when very few women were working for space agencies and in astrophysics. And she did some incredible pioneering work, and it was her who really developed the idea of space telescopes at all. So Hubble could not be named after her. It was the name was already selected, but with this one, NASA decided it's time to honor the mother of Hubble. So what better way to do that than to name Hubble's successor after her? And because it's more powerful and it's got basically 200 times the surveying capacity. And it's expected that it'll be able to conduct very, very in-depth studies of the universe from the earliest cosmological time points, directly image exoplanets. So see them directly rather than inferring their presence from the behavior of a star system or dimming patterns in a star. And in so doing, also collaborate with the James Webb so that you can figure they can characterize those exoplanets. So they're expecting tens of thousands of more exoplanets to be discovered and characterized within this decade, thanks to these instruments. And so, yes, to cover what some of them are going to be doing, between those observatories, and there are several more planned to follow, and there are several ground-based observatories too that are going to be operational in just the next few years. And all of them have a few things in common. They've got state-of-the-art advanced optics. They've got adaptive optics. They've got coronagraphs to block out starlight or interference from starlight, and spectrometers so that you can measure how the light is affected there. It has Fraunhofer lines. Basically, it indicates what chemical composition is being revealed by the light. And they are going to help in a process that is already underway, which is going from discovery to characterization. We have 4,351 exoplanets confirmed to date. And as of the other day, I checked, that number holds, and it'll be going up very soon. It is all the time. But yeah, they're going to add tens of thousands more as well to that inventory, and we're going to begin, astronomers are going to be able to sort through the stacks for years, finding which planets are habitable, which ones aren't. And the direct imaging aspect of this, being able to study them directly, that's something that we've barely been able to do so far. And it's so advantageous because not only can you tell by looking directly at the planet and seeing the light reflected off of it, not only can you tell what its atmosphere is made of, but you can search for biosignatures, which are various chemical compounds that we associate with life. So CO2 is a big one. Oxygen gas is a big one. Water vapor is another one. And well, the list goes on. And methane, that too, an organic molecule that is associated with life. And they'll even be able, based on the light that is being radiated and the light that's being absorbed, be able to identify land masses, oceans, and even vegetation. So finding vegetation on another planet, finding evidence of photosynthesis on another planet, that will confirm that a planet does in fact have life. That does have life. So potentially habitable will be giving way to inhabited. And beyond that, the really exciting possibility, obviously very much more far-fetched, but certainly possible, is to look for signs of technosignatures. So it's like biosignatures are signs of life, technosignatures are signs of activity. And that means intelligent life, at least as far as in terms of what we know life to be. And NASA recently released a report, and I recommend people go and look at it. I tried linking it here, here we go. I will just scoot this into the comments here. Okay. Whoops. Yeah. Anyway, I'll insert that in the chat there for everyone to see. The technosignature workshop outlined all of the possible technosignatures we could be looking for. Radio signals from space is the classic one. It's really the only one we've been looking for so far. It's considered a very viable one, but the purpose of this workshop was, let's talk about all the things that, all the means of communicating and technology that we know works. Not just the stuff that's tried and true by our standards, but stuff that we know will work for a civilization advanced enough. And so with that in mind, I put up these graphics here. This one on the top left is Coruscant from Star Wars. The one on the top right, that is what's known as a matryoshka brain, or a Dyson structure. Basically a structure that encloses an entire star and just soaks up its energy for all sorts of purposes. The one on the bottom here is an Alderson disk. And the idea there is that a species took all the material in its solar system and built a disk, flattened out around the star, which multiplies the amount of habitable space you have in a solar system exponentially. People are able to live on both sides of the disk, and the atmosphere is kept there because the disk itself is got so much mass it can simulate gravity. Now, as for plans to look for these signs of intelligence, these are all megastructures. They're a very fascinating one, but we're not really expecting to see those just yet. There's still bets open on whether or not Tabby stars because of a megastructure, but anyway, in terms of investigating for signs of technology and intelligence and civilization, there are several plans being mounted now. Now, the first two that I mentioned are Breakthrough Starshot and Breakthrough Listen. They're both part of Breakthrough Initiatives, which is a nonprofit organizations being funded by the Russian-Israeli tech billionaire Yuri Milner, and it's got Mark Zuckerberg on its board of directors, and it also had Stephen Hawking until he passed away, and several top-level scientists who are the chiefs in their field are contributing. So one mission they've got planned is Breakthrough Starshot, and that's going to go to Alpha Centauri. And it's a simple concept. It's a spacecraft that's about the size of a smartphone, but because of technology being what it is, that's big enough to hold all the instruments you need. Attach that to a massive solar sail, and then aim lasers at it and use those lasers to accelerate it. They predict that they can get it up to 20% the speed of light, so that it will actually be able to reach the Alpha Centauri system in 20 years. And it's got a tentative departure date of 2035, which means that it would arrive there by 2055. But you have to add 4 years four and a quarter years for the time lag on communication. So we won't actually be able to see exoplanets over there, if there are any. We know about Proxima b and a gas giant around Proxima Centauri as well, but not anything around the main binary pair just yet. So, yeah, by 2060, we will know for sure if there's any other planets there. And we'll get a chance to look at them, which will be extremely fascinating. Breakthrough Listen is another project that has been happening since 2016. And it is the most ambitious search for extraterrestrial intelligence project to date. And they've got multiple observatories who have made their data available, and they are sorting through the surveys that they make on a regular basis, using state-of-the-art machine learning algorithms that are trying to tease out possible techno signatures. And that'll run until 2026, and they've made several data releases, and more are coming. And then there's the Galileo Project. And Professor Abraham Loeb, who you may have heard of, he's the one who made the controversial suggestion that the interstellar object Oumuamua may have actually been an alien or an extraterrestrial spacecraft, and most likely in the form of a light sail or just a derelict piece of garbage. But he is, yes, he's one of the chair people. He's the chairman, actually, of the steering committee on Starshot, and he's now also the head of the Galileo Project. And it's being mounted through his alma mater, the Harvard-Smithsonian Center for Astrophysics at Harvard University. And they have essentially taken over the job of UFOs and unidentified aerial phenomenon after that big, huge data dump there that was done by the U.S. military rather recently. After that data dump, it's like, well, the military is no longer in charge of all this. The many, many, many years of reported sightings of unexplained things. Now it's the scientific community's turn. And so he's heading that up, and they're going to spend the next few years taking advantage of next generation arrays and surveys to try and see if any of the objects coming into our solar system, or any of the ones that are spotted in our atmosphere, could in fact be artificial. And from that, my denouement here is just really the question there. What do we expect to find? And we, of course, have no idea. We have hopes. We expect to find, top left here, exotic distant exoplanet surfaces, and also within our solar system, exotic environments on moons and nearby planets. We also plan to return to the moon. We hope to see cosmological evolution from the earliest periods and see how the universe truly began to take shape and how it changed over time. And from that, be able to come up with a more perfect sense of physics. And, well, if possible, we also hope to find extraterrestrial signals or some proof that we're not alone in the universe. And if I were a betting man, I would say if we do find a signal, we're not likely to be able to ever understand it, and the civilization may be long dead from any message we get. But it would resolve that question once and for all. No, we're not alone. They may not be here anymore, but there's got to be others. So that's my thought. And that's all for me. I apologize for going over time. I'm not looking at a watch, but yeah, that was definitely over time.
You're good. You're good. Thank you for a wonderful talk. If you want to stop sharing your screen, then we can get some Q&A going.
Yep.
Perfect. Okay. So AOT as a concept, it's all about you guys, the speaker. I want to ask you just a couple of questions about yourself before I get to the questions from the chat, and it also gives everyone in the chat just a little while to get their questions in. So the first thing I want to ask you is you a little bit about your job, your actual work. So since you're not doing research, we get a lot of researchers at AOT. Mm-hmm. You're more of a writer. So could you tell us something about what a normal day of work looks like for you?
Yeah, sure. Well, basically, the publications I work for, we either have assigned stories which we're then, tasked with looking into, researching, scooping, and talking to the researchers responsible, and then writing on it. And of course, there are other times there where, of course, it's we're contacted by people directly who are involved in various forms of research. And I mean, over time, of course, we'll make connections to the scientific community so that they will send out alerts, and we'll be on their mailing list because they know who we are and they want to keep in contact with science communicators. But yeah, whereas the researchers are the ones doing the legwork and pushing the boundaries, trying to figure things out, testing theories. Yeah, we're the ones who get to hear about it, generally before others do. Our job is basically take this, make it accessible to people because this is very important, but most people don't really have time to do the necessary research. And not everyone has a background in this sort of thing. Yeah.
So you are schooled as a historian.
Yeah.
Do you feel like, do you ever read papers and you're like, I have no idea what this means? How much of that do you actually come into contact with, and how much do you reach out to the authors and ask them what's going on?
Well, I almost always reach out to the authors. That is to say, if all we have news-wise is, this paper recently appeared, obviously we're going to talk to the researchers. Much of the time, news is filtered through, if we're talking about space agencies, they have their own PR departments. They're constantly putting news out there. But they, of course, are depending upon the SciComm community to basically read this, digest it, and convey it to the public. Basically help it go viral, and also to have something to say on the matter. Yeah.
Okay. And you also write science fiction, that's correct, right?
Yeah.
Do you, as a writer, feel like it's important that sci-fi be realistic, or do you feel like it can be a bit more like fantasy? No?
Well, I don't see the problem in having science fiction that is more fantastical. I mean, sometimes you have to. There's a lot of stuff I've liked since I was a kid that was not realistic at all. Personally, I'm committed to writing science fiction that's realistic, because it's like there's so many very interesting things that will be possible in the near future. You almost don't need fantastical elements really to explore it, but interests vary. It's just I do think that far too often people mistake sci-fi fantasy for reality, and that's unfortunate. But then you can't blame the genre for that. I mean, people do that with everything.
No.
Yeah.
So last thing on the topic of science fiction fantasy, we have a question that we ask every speaker at every AOT, and that is, what is your favorite Pokemon?
Pikachu. The only one I know. No, I'll be honest. Yeah.
That is totally fine. Totally fine.
Yes.
Just one of those.
I choose Pikachu.
Okay, so now for some science questions, and I'm going to ask the first question while I look up everyone else's questions, because I didn't write one down. So I do really appreciate you giving us a really broad overview of all of the upcoming and current space exploration missions. So I wanted to ask, which one is your favorite?
Wow. That's a good question. I think, well, right now I'm definitely leaning towards the James Webb Space Telescope. I don't know if anyone heard, but it's been the subject of a little controversy lately. Yeah. You've heard? Oh, good. Yeah, good to know. The less I have to explain, the better. But yeah, the name has garnered a little controversy. But Just what it's actually going to be able to reveal. There's so many unanswered questions when it comes to exoplanet research, cosmological surveys, dark matter, dark energy, and so forth. And the fact that it's actually going to move the ball on all of those, I think, is really cool. I'm also very excited for. I'm very excited about SpaceX, frankly. the Starship and its ongoing testing and the ability to launch, do orbital refueling and all that. It's amazing what's gonna do. What I'd really like to see, though, I have an article coming out in a few days about this, a space elevator. Yeah, and I don't want to give any spoilers here, but I've been talking to scientists who now are firmly committed, saying, and they're experts in their field, so when they talk, I listen. They say we've solved the materials problem, right? For anyone who's looked into space elevators, it's like, well, what about the tether material? That's the big problem. It's like, well, not anymore. So they got that linked.
Very interesting. Okay, so I'll start with some questions from the chat. The first one is from Stephen Dorsher, and he asked, just a little bit confused about Artemis and SpaceX's role. So I hear SpaceX has a moon contract, but NASA is doing the gateway. So how does SpaceX Starship interface with NASA for Artemis?
Well, what's this person's name?
Stephen Dorsher.
Stephen. Well, first, Stephen, I want to tell you your confusion is very justified. The last few years have been very confusing, mainly because I don't want to get political, but let's just say I blame Trump and Pence for everything here. But too political. Anyway, it's just pushing around the deadlines and so forth. SpaceX has found its role being inflated, right? So they will be launching, this is absolutely firm, they will be launching the first two elements of the gateway, the core elements of the gateway, in 2024 with a Falcon Heavy. And the idea there was if SpaceX can do that, we can focus on getting astronauts onto the lunar surface there with our launch vehicles and our spacecraft, because we can't deploy the gateway and land by 2024. It's way too much. But in the last few years, SpaceX was among three finalists, and this is why Jeff Bezos sued. They were among three finalists who were contracted for creating a lunar lander. And this was, in some cases, it's like, okay, so this will be something that NASA can launch with its rocket, or the private contractor can launch it themselves with their rockets. And for SpaceX, that was their lunar Starship, the Starship converted into a lunar vehicle. And it seemed pretty clear. The idea here is that if we can't have the space launch system ready in time, then we'll just let Elon launch our people using his thing. And of course, Bezos was just very upset. There's supposed to be two finalists. NASA narrowed it to one, kind of, without notifying people correctly, and that was that. So, yeah. Anyway, that's going to all unfold as we get closer to what actually SpaceX will end up doing. Sort of remains to be seen, and it's evolving very quickly, because that's 3 years away, and they're not likely to make that deadline. Okay.
Okay, next question is from Fred Sunderman, and he asks, I wanted to know this too. We heard there were some issues deploying the solar panels on Lucy. Do you know anything about that?
I heard about that. Unfortunately, another author was covering that, and that was today. I wish I could tell you more. I don't know the details, unfortunately. Apparently, there's been an issue with it launched. It's out there, and hopefully that's just a technical glitch and they can fix it. Because it would be a real shame if they had to, alter the mission or scrap it altogether. That would be horrible. But I'm sure it's just a technical glitch.
Okay. The next question is from Tabby Boyajian, and she says, "Great talk. Do you think we will find life in the solar system or outside the solar system first?"
You're the expert. Oh God, that's like a game of Russian roulette there, right? I'd like to. I will place my bet on in the solar system, and if we don't find it by probing deep enough into the Martian under subsurface there and finding some, bacteria and whatnot there, then I will bet good money that the Europa Clipper, Juice, and the Europa Lander find something, and they will do it by the early 2030s, right? Which I think will probably be before we find any techno signatures. Oh, and if there's still ambiguity on Tabby's star, I haven't really been keeping up with that. If there's still ambiguity, I'd love to know, because I don't ever want them to figure out what the hell it is. Yes.
Let it be a mystery.
Mm-hmm, exactly.
Just a couple of more questions. One is from Ali Chris, one of our streamers, and she says, "I also studied space age history in undergrad. I'd like to know your thoughts on comparisons of space colonies to 19th century mining towns."
Oh, I know that one. Yeah, that's a very valid question. There's a lot going on right now that people who are familiar with history there, who study history, they are thinking, I'm smelling a lot of age of imperialism coming off this plan here. It sounds like, we're going to get SpaceX is going to become like the East India Company, or the Hudson's Bay Company. It's going to be colonialism and of another form, and it's going to be just cutthroat. Well, yeah, I get that the concern, and I actually have been talking to the Space Court Foundation and the Space Generation Advisory Council, who are part of they're connected to the United Nations Office of Outer Space Affairs, or UNUSA. And they're putting in the work right now to try and ensure that doesn't happen. It's like, we want to solve all these legal issues of sovereignty and resource use and ownership and so forth ahead of time, so we don't run into this problem down the road. And yeah, I really support what they're doing, because of course it's like, if we don't have a legal framework, then that is something that could happen. Yeah. Right. Mining towns on the lunar surface, on Mars, on asteroids, and companies using all kinds of cutthroat techniques to control the shipping of resources. So I'd like to think that we're going to avoid that we are actually going to have a framework set up so we don't end up in a age of imperialism 2.0, because that really sucked.
Alrighty. So I'm going to do one more question. There are a few others that are in the YouTube chat. If you wanted to go onto our YouTube channel and ask them yourself, that is totally a good way to do that. But our last question is from Alex, our other streamer. And he wants to know what kind of music you think they would play in the space elevator.
Oh, wait a minute. Do I know you? We talked, I remember having a conversation like that. Somebody asked that, and we were debating that. Well, if I'm being realistic, I'd say they'd definitely be playing, some Muzak or Golden Oldies or whatever satellite streaming service they got there for music, and it's probably going to be all retro 90s and whatever becomes retro in the near between now and then. So probably that. But if I had anything to say about it, it's like, can we please let's get some classical music going. Space-related classical.
There's a lot of it.
Sorry?
There's a lot of it.
Oh, yeah.
A lot of
so Holst's The Planets, also Sprach Zarathustra, that's the theme music from 2001. See the monolith behind me? Great movie. And Shostakovich. Yeah, some of that. And failing that, let's get David Bowie in there, and anybody else who sings about space, let's get that there. Let's keep it thematic.
I'd like to just mention that our other speaker, Hannelore, said David Bowie in the chat.
Excellent. Good taste. Right.
Okay, so with that, we are going to head to an intermission. Thank you so much for a wonderful talk, Matt.
Well, thank you.
Before we break for intermission, I would like to humbly ask everyone who's watching to consider donating to our Venmo or PayPal. If you do, please let us know in the comments your answer to this month's tip war question, which is, would you rather defend yourself against asteroids with a giant laser or a giant trampoline? But we will be back at 8:10, so I'll see you all then. everyone, and welcome back to the second half of our October Astronomy on Tap here in Baton Rouge. We're just going to get right into it. So our second speaker today is a graduate student at CU Boulder studying black hole physics, specifically regarding quasar fueling. You may have seen them in the documentary Behind the Curve, where she discussed flat Earth theory. You can also follow along on her Twitter if you want near daily updates on their two adorable dogs. And here to tell us why black holes don't suck and why they're bald, I am happy to introduce Hannelore Gerling-Dunsmore.
Thank you so much for that introduction. Give me 1 second. I need to figure out how. 1 sec. Things are going to be this way. All right. Got this. Let's go ahead and get that going.
Love the pink.
And thank you. Yeah, it's always pink. All pink everything. All my candidacy plots are like in pink and purple, and I absolutely refuse to allow my advisor to suggest that I change it to something different, and he knows how stubborn I am, so we need more of it. So let's go ahead and get started. So again, thank you, Astro on Tap, Baton Rouge, for having us here tonight. It's wonderful to get to talk to folks about black holes again, other than my advisor. And thank you everyone for tuning into the live stream. I just want to say you are all huge nerds, and I think that is awesome. So tonight I'm going to be talking about black holes and what I see as kind of the basics for understanding them and what they have going on. I think it's going to be a pretty fun 25-ish minutes. I do tend to run a little bit long when I'm talking about black holes, but hopefully I have a timer on because I have never once been on time with a talk. So we'll see how this goes. All right, so I think a lot of people are familiar with the basic concept of black holes, which is them being these things in space that things fall into and then can't come back out of. A more rigorous definition of a black hole is an object that has a strong enough gravitational field that light can't escape from it. And a question I sometimes get is, because I teach a course actually about black holes here, well, I TA, a course about black holes here at CU. So I get this question a lot because I teach this course a lot, which is, why do we use a black hole's effect on light specifically as its defining attribute of black holes rather than some other particle or some other object? And that's a really, really great question, actually. And it gets to a really fundamental aspect of black holes. So in order for something to leave an object, it's the energy of its motion, its kinetic energy, has to be large enough to be greater than the gravitational energy of the object that it's trying to leave. So basically, something has to move really, really fast to get away from something really massive. A way to kind of intuit this is if you are on a skateboard at a skate park, if you're going too slow, you're going to just roll right down to the bottom of the bowl. But if you're going really, really fast, you're going to skate right on over the lip of the bowl and keep on going. That is literally the exact same physics. Well, more or less. To first degree, it's the same physics. And so, the big thing is the faster you're going, the easier it is to escape something's gravitational energy or gravitational force. So nothing can go faster than the speed of light. That's something that's been established. And honestly, I could take up this whole time explaining why that is. So instead, I'm going to ask you to trust me that that is a thing that we know very, very well. And so nothing goes faster than the speed of light. And so if light can't escape an object's gravitational force, nothing else is going to escape an object's gravitational force. And so a black hole is just the one object in the universe that even light can't escape. So, so 1 second, sorry. There we are. All right, so I like to say that black holes are the closest thing that our universe has to Eldritch abominations, because I'm super into horror. So, but the thing is, it's kind of true, right? They have this unique singular effect, which goes way beyond anything that we have ever evolved to have an intuition for. Things fall into a black hole and they essentially stop existing. And there's nothing else in the world that is the case, where just you fall in and you're not there anymore. So they're all inspiring in kind of this like true biblical sense, and also kind of terrifying, which makes them perfect for our October Astronomy on Tap. And I think that's part of why they're such a popular plot device in a lot of science fiction. So I think the most widely known use of a black hole as a plot device was in the movie Interstellar. And as an interesting side note, actually, really quick, the appearance of the black hole was actually more or less scientifically accurate in the sense of the light from behind the black hole getting bent up over the top of the black hole. Again, this is another thing that I could spend my entire time tonight talking just about that. So instead, I'm going to direct you to the Veritasium video that he put out right around the when the Event Horizon Telescope was, announcing its first image, because that explains it in really great detail. So, but yeah, kind of a fun fact about that. So another physics plot device in Interstellar was time dilation, which they got less right than the behavior of the light near the black hole, but they still got pretty right. To be, just to be clear, they still got it pretty right. And that ties into a question that I also get all the time when I am teaching, and also from my brother, which is, can you use black holes to time travel? And the answer is kind of. So what do I mean by that? Before we can actually get into what I mean by kind of, we first need to talk a little bit about relativity. And a lot of times when I tell people that I'm going to talk about relativity during a SciComm talk, people say, oh no, but what about the math? And I say, you don't need math to understand relativity. You really, really don't. You need math to be able to calculate things that are relativistic, but you don't need it to understand the physics of it. So, I know that there's probably a reaction of like, oh no, like this is going to be so complicated. I'm not going to be able to follow it. Trust me, like I have taught relativity to over 1,000 people. So just come with me on this. I promise that if you don't get too stuck in the, oh no, it's relativity, it's going to be confusing, you're going to come out the other side of this in like 5 minutes, actually, having a pretty intuitive understanding of relativity. So with that said, let's go ahead and get going on that. So what I have here up on the slide is a little cartoon of a thought experiment that is called the light clock. And so here's how it works, is it is, we know that light travels at in a given medium, it always travels at the same speed. Our light clock is filled with just like basic air. So our photon is traveling at 3 times 10 to the 8 meters per second. That is always what it's going to be traveling at. And that is a really important part of this. And so we can define a unit of time from this photon leaving point A, this bottom mirror, up to point B, which is another mirror, and then back down. That's our unit of time, okay? And there's some distance L. The photon travels 2L in that time, 1L up, 1L down. And, so you can go ahead, you can calculate that, you can get a concrete number, and that is your unit of time. And with the malice of forethought, I'm gonna call that dt of photon. Now, why did I say a photon? Well, we will get there. So, in just 1 second, there we go. So now, if you were standing outside the light clock and the whole setup is moving to the side, there is an interesting effect. From where you are standing, the photon starts moving up towards the top mirror from the bottom mirror while the box is in one spot, but the whole setup, photon included, has to move over to the side as the box moves. So it has to kind of chase that top mirror in order to get up to the top. And then once it hits the top mirror, it has to chase the bottom mirror back down. So you end up actually getting, instead of just straight up and down, you get a triangular path for this photon, right? And, going back to whenever you took geometry, the hypotenuse of a triangle is going to be longer than just one vertical side of it. So this is going to be a longer path. Now, if the box were moving really, really slowly, the photon is moving so fast that by the time it goes up and down, the box hasn't moved really any sort of significant amount. But if the box is moving horizontally at a speed that is pretty close to the speed of light, in the time that it takes for the photon to move up to the top mirror, that box is going to move a substantial amount to the side. And then likewise, in the time that it takes for the photon to bounce down to the bottom mirror. And so we end up seeing that that photon is taking a longer path. But again, remember, that photon is still traveling at the same speed. It can't travel any faster or slower. And as a result, we end up seeing a longer unit of time because, again, longer distance, same speed, that's going to be a longer amount of time. We're going to go ahead and call that dt of us. So, of course, the photon doesn't notice any of this. And if you're like, oh, Hannelore, why is it not noticing any of it? Well, the answer is, let's say that you are sitting in a car that's going up at a constant speed and you're tossing a ball up and down because you're really bored, because, you know, car rides are really boring. You don't see the ball going in a, you know, triangular path. You see the ball just going up and down. It's exactly the same situation there. So the photon just sees itself going up and down, but the photon sees itself going up and down even while the box is moving to the side, but you, outside of the box, see this triangular path. And so, putting together, the only logical conclusion, which doesn't seem that logical at first blush, which is, you know, the photon sees a shorter amount of time go by than you do. And ultimately, this isn't just a cute thought experiment. This isn't just a neat what if. This is actually a real measurable effect. Your GPS has to take it into account, actually, when they're programming your GPS. And this effect is called time dilation. And so you see things that are moving faster than you as experiencing more time than they see themselves experiencing, which means you see them kind of living in fast forward. The light clock experiment I just described is technically an example of special relativity, which is relativity in the absence of gravity, but the same result holds in a gravitational field. To get information for why that happens, imagine that this mirror is getting stretched rather than moving to the side. It's the same deal. You still get the triangular path instead of just straight up and down. And as a result, if you're near something that's really massive, you will also experience time dilation, which means you will see the rest of the universe living on fast forward, basically. So more concretely, if you're near maybe a black hole, for example, you might only see an hour go by, but the rest of the, someone back on Earth might see like years and years and years go by. And sorry for the mild spoiler, but it's also been a lot of years since Interstellar came out. That was a major point of the plot device, one of the major plot devices in Interstellar. So that's what that is. That's time dilation. And that's a major phenomenon near black holes. And it actually shapes a lot of stuff, which again, we don't have time to get into, but time dilation. So we're now going to loop back to this question of, can you use black holes to time travel? And my answer being kind of. Oops, sorry about that. So if you go near a black hole, time slows down, but it doesn't reverse. So if you go and you sit near a black hole, you know, you will be able to get transmissions from Earth that end up spanning a much longer period of time than you would be able to survive as like a human being. But you aren't going to be able to go back in time. You're just going to be able to get information from a longer range of times than you would otherwise be able to. So it's kind of like time travel, but not really. And you definitely can't go backwards in time if you're outside the event horizon. Now, if you get inside the event horizon, that becomes a different question. But we also don't have any models at this point of what definitely happens inside of a black hole, because we can't get information about what's going on inside of a black hole. Which brings us to the first part that I'm going to answer of today's title, which is, why don't black holes have hair? So again, we're going to go back. Black hole, nothing can travel faster than the speed of light. So no, you can't send any particles or anything out from inside of a black hole. The only information that you can get about a black hole is what properties are externally visible, basically these what we would call global properties. And that ends up being the mass of the black hole, the angular momentum of the black hole, so basically how fast is it spinning. And you could observe charge of a black hole, but the thing is that we've never observed a charged black hole, so but that means that there are no thermodynamic properties. So there's no chemical composition. There's definitely no temperature. There's actually no structure that we can see, because, the structure of, this green bean that I am tearing up and throwing to my dogs, it's frozen. So it's going to have a different shape than once it melts. So that also is actually a thermodynamic property. We can't observe any of anything, the net geometric structure of what a black hole has, what's fallen into a black hole. So you can only see those three properties. And as a result, you can say that a black hole isn't warm because it doesn't have any thermodynamic properties. So they don't have hair because, do you get it? Like they're not warm, so they don't have hair because hair keeps things warm. That's right. The no hair theorem actually is just a pun. It's just a big pun. But that's what that actually means. When we say that a black hole doesn't have hair, it means that the only properties that you can ever observe about a black hole are its mass, its angular momentum, and theoretically you could observe charge even though we never have. So, the one half of the title today is black holes don't suck. But you know what? I'm willing, or one half of the title today is, black holes are bald, they don't have hair. And the other half is black holes don't suck. And I am fully willing to admit that physicist humor totally does suck, but I am going to die on this hill. Black holes don't. Because things fall into them. They don't get sucked in. So what do I mean by that? So to suck implies that there's a negative pressure. So when you suck in a piece of spaghetti, for example, you're applying a negative pressure and that's what pulls in the spaghetti. That is not what's happening. The black hole doesn't do that. The black hole is literally, things just fall into it, just like a ball that you toss up falls back to Earth. So black holes don't suck. They just are something that matter falls into. Which, to some extent, people might say, what's the difference? And I say, there's a lot of difference. And one of the big differences is that it is actually really hard to figure out how matter falls into a black hole. If black holes were sucking things into them, it'd be a lot easier to figure out how things get into them because the black hole would be actively pulling them in. That's not really the case here. The black hole is just this doom ball out in space and things fall into it. So one moment. Now, what actually does happen if things aren't getting sucked in? What actually does happen when matter gets, brought towards a black hole? Well, one thing that is actually kind of interesting is that the matter that is what we say gravitationally captured, so that means the matter that is essentially going to fall into the black hole, it gets there's something called tidal forces, and tidal forces are when a given force, the strength of a given force scales with how strong you are from the object exerting the force. So in this case, let's pretend this yellow ball is our black hole, and this blue ball is matter that's become, it's going to fall into the black hole. As it gets closer, the gravitational force of the black hole is actually going to act more strongly on the edge of the blue ball that's closer to the black hole than further away. And it's going to pull it out. It's going to stretch it out, just like we're seeing here. And that process is called, actually, the technical term is literally spaghettification, or, one second, tidal shredding. And so anything that gets gravitationally bound to a black hole gets brought into the accretion disk around a black hole, which I'll explain in a second, is said to be either spaghettified or tidally shredded, which I think both of those are pretty equally funny terms. But it does mean, you can have a star wandering near a supermassive black hole at the center of a galaxy, and if it's not moving fast enough, it's going to get gravitationally captured onto that, to that black hole, and then it's going to get ripped apart. Which is a little bit grim. So I actually lied to you a little bit when I said that you could go sit near a black hole and watch, the universe go by, because you won't. You'll get tidally shredded into a plasma. You'll just be an ionized gas. So I'm sorry that I lied to you a moment ago. I just was trying to illustrate time dilation. I think it's a pretty good reason to lie. So this matter is tidally shredded, and something that's really important is that things in space usually have magnetic fields. And those magnetic fields don't go away just because the matter that they were attached to got tidally shredded. Sorry, one second. And so you have a bunch of magnetic fields inside these disks around black holes, which you can think of it as the black hole is the drain and the accretion disk is the water swirling around a drain in a bathtub. And the thing is that in order for things to swirl down a drain, they have to lose some amount of energy. That is to say, they have to experience viscosity, which is a fluid's version of friction. Friction is just something trying to oppose changes in its motion. Magnetic fields are basically like springs. and springs don't like to be compressed, they don't like to be stretched. And as a result, your magnetic fields end up preventing your disk from wanting to be compressed or stretched. Luckily, black holes have really strong gravitational fields, and so it happens. But basically, the reason what I'm all leading up to is that these magnetic fields are incredibly important because not only do they move matter through the disk, but when the magnetic fields get tangled up, it's like a spring that you compress, right? And when you compress a spring and then you let go of it, it springs apart, right? It's kind of a similar thing where you tangle up these magnetic fields that are going around in circles around these black holes, and then eventually they kind of snap apart, and you end up launching jets. And you launch these jets of radiation, which literally that's what it is. It's a focused beam of radiation getting launched out of the center of galaxies. And it's about 1% of all galaxies have this going on at any given time. And as Matthew told you earlier, JWST is going to be able to observe the earliest galaxies in the universe, right? Well, what JWST is going to be observing is the jets launched from the supermassive black holes at the centers of those galaxies. So we are literally seeing, and so the brightest of these black holes that are launching, supermassive black holes that are launching jets are called quasars. And the brightest quasars we have seen are over 13 billion light years away. So that means that they had to form within 1 billion years after the Big Bang, which sounds like a very long time. 1 billion years sounds like a very long time, but it is actually a very short period of time to make a supermassive black hole that is 10 billion times the mass of our sun and an entire galaxy around it. So that is actually an incredibly rich field of research right now, is trying to figure out how is it possible to grow supermassive black holes that fast, and how is it possible to build galaxies around them that fast. Because we are observing them, and we're going to be seeing more of them once JWST goes online. And hopefully it is going to unfold beautifully and is going to go great. And December 18th is going to be a wonderful day, even though I think every single astronomer and astrophysicist you have ever come across is going to spend that entire day completely terrified. But yeah, so it's kind of a neat thing. So these are some real quasars, by the way. These are not drawings, these are not illustrations, these are real quasars that have been images that have been taken of them using telescopes. So, final question. I've been talking a lot about how things can fall into a black hole. And this is another question that my brother asks me a lot whenever I tell him about my research. And it is a black hole going to ever eat us? And this one I can answer actually more definitively than the time travel question, which is almost certainly not. And here's why. You are only going to get most of the black holes that we know of in the universe are what we call stellar mass black holes, and they form through the deaths of massive stars. So stars, it's a big ball of gas. They collapse into a big sphere, and it starts out as just hydrogen and helium. And due to the mass of all of that gas just pushing inwards on itself, it actually starts shoving the molecules together hard enough to start driving fusion, where, if you're not familiar, fusion is this process of taking two molecules and you push them together, and they don't want to be pushed together at first. They want their space. But if you push them close enough together, some parts of them pop off and they form a new molecule. That's the fusion part. And the stuff that gets popped off of them, that releases a bunch of energy. And so that's what makes stars burn. all stars are undergoing fusion, but only really massive stars undergo enough fusion where you start off, you have hydrogen, it fuses into helium. Okay, that's fine. And then pretty much all stars end up fusing helium at some point. That's all right. But in really massive stars, you end up getting this shell structure where the outer shell is hydrogen, the second outermost shell is helium, then it's carbon, then it's oxygen, so on and so forth, until you get all the way to a little ball in the center made out of iron, which is essentially this ash being deposited by silicon fusing to itself. And what's really interesting is that these stars live for, 1 million years, 10 million years, somewhere around that. Once you start depositing that iron ash, within a few days, less than a week, within a few days, those stars will die. And here's why, is that all of that iron, you can't fuse iron because you won't get any energy from fusing iron. Iron is, this incredibly stable element. And so you just have this ball of iron that's getting more and more and more mass. And eventually you get so much mass that the gravitational force of that iron ball on itself shoves the electrons onto the protons, and those all become neutrons. And so instead of having these molecules in the center, you just end up with a big ball of neutrons. And there's a ton, that makes it collapse really fast. So it's just a ball of neutrons now, and that starts falling inwards, and it's no longer supporting all the outer layers. And so those start falling in. And actually, though, a really cool thing is that this ball of neutrons at the center, eventually, something really interesting happens, and this is not what we call is the nuclear force becomes repulsive. And if people have questions about that, they can ask that in the Q&A, but nuclear force becomes repulsive. So it no longer is collapsing in, matter hits it, and then they bounces back out. And most of these stars where that happens, eventually that turns into an explosion, and that's a supernovae. But for some of them, they can't explode. There's too much matter falling in, and that turns into a black hole. And so that is the primary way that you get what we call stellar mass black hole in the universe. And we have about 100 million of those just in our galaxy. And most galaxies have a similar number of them. So you get 100 million of these black holes, of these stellar mass black holes in a galaxy. Eventually, they run into each other. And so another way that we get slightly larger stellar mass black holes is the merging of two black holes. So while a black hole is unlikely to come and eat us in our solar system, black holes absolutely do come across each other and eat each other. And we actually have started observing that directly through observing the gravitational waves released by two black holes merging together. And that's what LIGO, the Laser Interferometer Gravitational Observatory, all of those results are just looking at the gravitational waves from two black holes merging. Well, there's also other things, but black holes merging, which is pretty cool. That we see. And so on the right, we see that's one of the sites for LIGO. I believe that's Livingston, down actually in Louisiana. So it's fun. One thing is there's actually been a significant problem for Livingston where they've had to try to figure out how to keep LIGO stable because people keep coming across it and shooting it because it's just a large concrete tube in the woods. And so I guess people just shoot it. So that's been something that they've actually had to work on because it getting shot has caused some issues for the scientific observations. That's just a fun bit of color for all of that. And so, again, all these things, I'm telling you why I don't think it's going to be an issue. First of all, our sun is absolutely not anywhere near large enough to leave a black hole. And that's actually important because the more massive a star is, the shorter its lifespan will be. And so it's actually not an accident that we ended up evolving in a solar system, in a planetary system around a very low mass star. Our sun has one of the lowest masses that you can have and still have fusion. And so that star is going to live about as long as a star can live, which means we've had more time to be able to evolve. So that's not an accident that we're around a really low mass star. And really high mass stars are disproportionately at the center of galaxies in what is called the Galactic Bulge. And so more black holes are going to be towards the galactic center. You're still getting stellar mass black holes in the arms of a galaxy, but they're not very densely populated out where we are in our galaxy. And another thing is that every massive galaxy has a supermassive black hole at its center, which a supermassive black hole is defined as a black hole that has a mass of 1 million solar masses or larger. That was what the Nobel Prize was given for in 2020, I believe, was the discovery of galaxies having supermassive black holes at their center. So that's kind of neat. And yeah, so to finish this up here, why don't black holes suck? Well, because they don't they don't things into them. They don't suck things into them. Things just fall into them. And I also think it doesn't suck that they are unlikely to eat the Earth. I think that is actively pretty cool. It does a little bit suck that you can't use them for time travel, but I still think they're pretty neat. And then why don't black holes have hair? Well, what the statement black holes don't have hair means is that there's only 3 properties you could ever observe about a black hole. Its mass, its angular momentum, and its charge. You can't observe any thermodynamic properties. So black holes don't have hair is just a pun. There aren't any warm properties about them. And also, you know what? I think it's a black hole's personal business about what they do with their hair. You know what I mean? I think we need to respect that a little bit. So on that note, I think it's time to open it up for questions.
Yes, it is. Thank you so much. If you'll stop sharing, we can get the Q&A going. Yes, I am both simultaneously surprised and not surprised to hear that something that I had no idea what it meant was just a pun in astronomy. That's just about as on brand for astronomers as you can get. So
I know. Sometimes I feel a little bit bad because I'm like, I feel like it's anticlimactic that it just turned out that it was a pun. But on the other hand, I think it's kind of fun. And I think that pun really helps drive home why it is that those are the only three properties you can observe, which are they're the only thermodynamically independent properties. So,
right. Yeah, well, I wish I could write that on my undergrad exam. But
I would give you full points if you were in my black holes class.
Okay, so just a few questions about you, and for all of our audience members, go ahead and put any questions that you have in the chat and I will ask them shortly. But some questions about you. What got you into astronomy?
Oh gosh. Okay, so this is a super cheesy answer. But a lot of people are like, when I was a little kid, I looked up at the night sky. But that's actually a real thing where I grew up in the middle of nowhere. I grew up in a very, very tiny town in Maryland. And we had very low light pollution. And my parents also didn't really want me watching a lot of TV because, so my mom and I at night would instead go out and we would look up and my mom would point out what the Milky Way was and all these different things. And that became kind of our big bonding thing, like mother-daughter bonding thing. And then I started homeschooling after elementary school. And I went to, my mom would still take me to field trips because she thought that was important. She took me to a science museum when I was 11, and the display or the exhibit was all about space. And I walked around there and I said, why is everything in space a disk? And I went, I don't know, Hannah. That's a good question. And actually, it turns out that that's now my research. And the answer is because angular momentum throws things out into disks. That is the answer, everybody. That's why things in space are disks. That's why galaxies are disks. That's why accretion disks are disks. It's why planets and stars collapse out of disks. It's because everything has angular momentum. And angular momentum throws things out into a disk. Just like if you were to take some pizza dough and throw it with a spin, it turns into a disk. That's why. So, you know what? I already answered it. Now I'm like, oh, sunk cost. I had that question when I was 11, but now I gotta keep going. So that's the answer on that one.
I do, in fact, tell all of my students that it is because pizza dough exists.
Yeah, no, it's literally pizza dough. Like if you want to know why things are disks in space, just make some freaking pizza and you have your answer.
Okay. What is your favorite part of being an astronomer?
I love almost everything about being an astrophysicist / astronomer. I don't think that I deserve to be called an astronomer because I don't know how to work a telescope. I really, really love getting to read. So I obviously have to read a lot of papers, to inform what I'm doing. I think that is awesome that a major part of my job is just sitting there and learning about this cutting edge science. I love the fact that a major part of my job is sitting down and getting coffee with really smart people doing really interesting things and just getting to ask them questions about what they're doing. And I love the fact that, for a little bit of time, a lot of my work, I'm a theorist, so I pretty much do math and I run simulations. And I love the fact that when I am done with a calculation or I pull down the results from my simulations for just a moment of time, there's a little bit of something about the universe that only I know, that I'm the only person, well, certainly the only person in the world knows, is that there's this one little thing that's just for me. And of course, then I emailed my advisor and I said, I did science. You should be paying me. But there's a little moment where it's just for me. And that might sound a little selfish, but it is we all have to work for a living. And it is a very special thing to be able to work for a living, and part of that job being sitting for a few moments and knowing something about the universe that nobody else does.
All right. What are your hobbies outside of astronomy? Everyone has other
Oh
lives.
gosh, there's a lot. So I currently have 80 something houseplants. So I have a lot of
My
plants.
camera around, but
I have a lot of plants, and I'm really into plants. I have my dogs who I love, and I love training them and teaching them new tricks and stuff like that. One of my best friends is actually a researcher in dog cognition and dog learning, like how dogs learn things, using them as an analog system for how humans learn things. But anyway, so she'll tell me all these things. I'm like, okay, I gotta try stuff out on my dogs. I love horror, actually. I watch a lot of horror movies. This year I've been working on my candidacy, my research for my PhD candidacy. So I've dropped off, but usually I watch between 50 and 100 or more horror movies every single year. So, and also in addition, horror TV series, horror writing, horror podcasts, just a lot of spooky shit. And I like to cook, in particular risottos. So
nice. Okay, I have to ask.
Mm-hmm.
You know that dog with the buttons, the like doodle? There's like a golden doodle who talks to their owner with buttons.
Oh, I know the Aussie sheepdog, the Aussie Shepherd, Flambeau, who has the buttons, like a huge sheet of buttons, and he can like say like he wants pets, he wants treats. Yeah, I've watched Flambeau's stuff a lot.
Okay, yeah, those are crazy.
Oh, it's incredible. It is incredible what dogs can learn.
And then our last question about you is the usual question that we ask everyone, and that is, what is your favorite Pokemon?
There is a cat that in my life who I love very, very much named Shinx. And so Shinx is my favorite because Shinx is a wonderful girl. She's a very sweet baby.
Perfect. Okay. So we will transition into some sciencey questions. There was a bit of discourse in the chat, and it actually relates to the question that I wanted to ask. So I wanted to just have you clarify. So I personally am under the impression that quasars, and by extension all active black holes at the center of galaxies, go through activity phases where they're like on and off. Could you just talk about that and kind of how it works or what we know about it?
Absolutely. Well, the good news is this is a short answer because we know very little. So what we are pretty sure of is that all supermassive black holes at the centers of galaxies are active at some point. When we look out to the night sky, about 1% of galaxies we observe have active galactic nuclei, have black holes that are launching jets. And so what we think is that it's approximately 90% of a galaxy's life is spent quiescent, not active. And then about 1%, its center is active. Now, you asked me, what makes it be inactive? Buddy, if I knew I would have tenure. I would have all of the grants. I would be sitting on top of grant money like a dragon. But what we think it has to do with is the accretion disks around black holes, which is why I actually wanted to talk about accretion disks, even though I know it's always hard to decide how much you're going to talk about accretion disks when you talk about black holes in SciComm, because accretion disks are actually incredibly complicated. But the thing is that pretty much every interesting observation about black holes has to do with the accretion disk. So I always try to bring them up a little bit. So going back to those magnetic fields that I was talking about, magnetic fields do provide this kind of, this viscosity, this fluid friction that allows matter to move in towards the black hole. But they also, it seems, based on the models that we do and the math that we do to them, is those magnetic fields can get into configurations that can actually hold the matter from moving in through the disk. Is kind of the simplest way I can explain it. So basically, it is a very active area of research and actually something that I work on. Well, my work is indirect or is fairly closely related to, and the idea is to build it out to apply to this, the process of what makes matter move through an accretion disk, and as a result, what changes in an accretion disk to make it go from being active to inactive. So 1 second. Here, guys, quiet. We don't have to put our green beans. There's plenty of green beans. The boys are my boys love their green beans, and they got very grumpy that they tried to go for the same green bean. That did not go well. We're okay. But yeah, so that is a fantastic question, and I'm sorry that I don't have a more concrete answer, but basically the answer is, I don't know, the magnetic fields do a thing, probably.
Fair enough. Okay, the next question is from our other speaker, Matt Williams. He asks, can you explain the black hole information paradox?
Absolutely. So I actually took that out of this because I was like, I'm gonna go down a rabbit hole if I talk about this. So I am very glad that you asked this, actually. Thank you, Matthew. So as I said, we can only extract, the only thing we can observe about a black hole is the net amount of mass and angular momentum and theoretically charge, even though we've never observed them to be charged, that has fallen into a black hole. And so the question becomes, is all of the information, all the additional information, the chemical composition, the temperature, the net temperature, the blah, 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 does that all persist and still exist on the interior of the black hole? Or the current alternative model is something that they call firewall, where basically through these processes that I do not understand well enough to explain without math, everything else just basically burns up on the surface of the black hole. And so if you have that information persisting into the interior of the black hole, that becomes this kind of weird thing of like, well, where does it go? Why can't we get, we know why we can't get it, but then what are the implications for that in terms of information theory, da, da, da. And so it is in some ways cleaner to say that, oh, it just disappears. But the issue is that if we get into something called the Einstein equivalence principle, which is this idea, there's a lot of things. There's a lot of parts of that. But the relevant part of it is that something that is crossing the event horizon of a black hole, that if it magically weren't tidally shredded, wouldn't notice a difference. Because to it, this is just how the universe is. And so what's kind of at odds is, according to the equivalence principle, something should be able to cross through the event horizon without it itself noticing. So that would imply that its information is carried over into the black hole interior. Whereas like information theory would say, it's got to go somewhere. Where does the information go? It goes burn. Firewall. And so the answer is that we don't know. There's some models of black holes like called soft hair that kind of try to thread this needle and try to say, oh, well, da, da, da. The answer is ultimately, I think, the most honest thing is we have no idea because nothing has any empirical support. And so everyone is just building their house of cards on the table of mathematical consistency. And so there's a few different options on that. Okay. Again, another question where the answer is, that's a great question. Let me just give you a bunch of
I have a feeling that's how these other questions are going to
That's okay. It's fun. It's fun. I like sharing what the current, parameter space of potential explanations are. Even if my answer is still, we don't know which of these, or maybe it's something even more wild, but currently we think it's one of these. I think it's really fun. I just want to be very clear. Like, I am not saying that one of these things is more likely than the other. We don't know right now because we don't have empirical support.
Okay, so we have two more questions. One of them is from Stephen Dorsher. He asks, has Hawking radiation been observed yet in any physical situations? Or is that maybe not possible due to accretion disks?
So yeah, that's actually a great question, Stephen. We haven't observed Hawking radiation precisely for the reason, well, partially because we just don't have the resolution to observe them anyway, but also because just like if you try to take a photo when there's a super, super bright source of light, it's going to overexpose your photograph. Same deal, the accretion disk and the jet and the winds and all that. Tear, can we stop barking at our neighbors, please? Tear. Thank you, sweet boy. So yeah, even if we did have sufficient resolution, the accretion disk is just so much brighter. However, the physics that predicts Hawking radiation is pretty well tested, and so it is very, very likely that it occurs. The thing to be aware of is that Hawking radiation is incredibly slow, and even the smallest black holes that we are aware of how they could form it would take longer than the age of the known universe for them to evaporate, which is to say lose all their mass to Hawking radiation. So, Hawking radiation is an interesting question or an interesting topic in the context of, end game cosmology, which if you want a really great discussion of that, The End of Everything, I think it's The End of Everything by Katie Mack. Wonderful book, really wonderful book. And she's a wonderful person. So just plugging that there. But yeah, so my answer to that is Hawking radiation is likely correct because the physics that it builds off of is pretty well tested, but we have not been able to observe it exactly for the reasons why Stephen asked and it's because the accretion disk and everything near the black hole is just so much brighter.
Okay, and then our last question of the night, seeing as how all matter is mostly empty space, what do you think is the composition of a black hole?
Eldritch Abomination, I don't know, man. Like a great old one, I don't know. Spooky shit. And so here's the thing, I'm saying that and it sounds flip, but actually my answer is I have no idea. Because again, this is something that if someone were to, really, really push me for Honolulu, what are your opinions about what a black hole is made out of? I would say that is a question that has multiple interpretations. So one would be, a star is made out of plasma. It's made out of hydrogen, it's made out of helium towards the end of its life. If it's really large, it's also carbon and silicon, blah, 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 blah. But it's made of something. The Earth is made of chemicals, various chemical compounds. It's made of these things. I don't know if I would say a black hole is made of something in the same way. And that's part of what is so staggering about them, is that black holes aren't so much made of something so much as, and again, this is actually something that's really unique about black holes. So I'm so glad that we got this question, which is most things in the universe, everything else in the universe that I can think of is made of something, right? Whereas a black hole is more defined by what it isn't. A black hole, if you imagine, there's a pretty classic picture that I didn't include because I think it tells a story that isn't entirely true, but it's this picture of, a flat sheet, and then there's a hole going down with the vertical walls. It's called an embedding diagram. And that's kind of what a black hole is, but keep in mind that it's that from all directions. So it is a sphere into which all of space-time, if it's not ripped, it's effectively ripped from our perspective outside of it. And so I would say that what's really interesting about black holes is that they're not made of something in particular so much as they're not defined by what they're made of, but rather by what they do. And that's why in the beginning I was talking about their effect on light. And so this is actually a very, very deep question that got asked there. And my answer is I don't know if we can define a black hole by what they're made of. Because again, that's a kind of a thermodynamic property. And so that gets into the research realm of black hole interiors. So my answer is black holes are weirder than matter.
All right. Well, on that note, I want to thank you very much for a wonderful talk, and thank Matt as well. So yes, thank you very much to both of our speakers who very graciously volunteered to come talk to us today. We know you're both really busy, so thank you very much. I also want to shout out our streamers who are behind the scenes and aren't seen, Allie and Alex. They work really hard to put this show on for us. So before we head out, just a few last minute things. If you are watching us asynchronously and not live, do please feel free to still interact with us. Subscribe to our channel, like this video. You'll get notifications for our next show. And keep an eye on our Facebook, Instagram, and Twitter. We post about all of our events as soon as we have information. And I do actually have information for you that our next show is going to be on November 18th. So keep that in mind. But we will see everyone here on YouTube next month, where we will have 2 more lovely speakers for all of you. Until next month, goodbye.